So here's kind of our agenda. So the things we already know, just getting you back into our mind frame. We do data mining processes, we've got categories, we've got all these different tasks we've been doing. We're just going to keep up with that. Now we're just going to add in a new methodology, right? So at this point, you guys can do supervised tasks of linear regression, logistic regression, k-nearest neighbors, decision trees. We've done all of these. We've got unsupervised tasks with your visualizations, which overall, some interesting visualizations on your last project. We've done some principal components analysis. We've clustered. We've done, you guys just completed or are completing your association analysis homework. So we've done supervised and unsupervised. We've got two more supervised methods that we're going to learn this semester. The Bayesian networks we'll learn today, and neural networks, which we'll talk about next week. And that's kind of going to be your big foray into what we'll call data mining. So again, your assignment's not due yet, so we can't really discuss this, but your big goal for your association assignment is coming up with 3 rules. I don't care what they are, as long as you have output that supports them, and you can tell me why you picked them. All right, that's kind of task 1. What are your 3 rules? Okay. And then the last thing, task 3 maybe, is your elevator pitch. So just a friendly reminder for your elevator pitch. It's not very long. You just want to hit the big ideas. What was your business question you came up with? What support? So giving your rules. How are you trying to answer this business question? And then make sure that you kind of leave with a recommendation. It doesn't have to be the most insightful thing in the world, but just a conclusion, a couple of sentence conclusion for the recommendation. Make it a pitch. Should be pretty much a standalone document. So your paragraph or 2 should be pretty standalone. Don't be referring me to figures and things like that. Right? Use the figures to make your argument, absolutely. But just be able to kind of talk about it. Nice, concise, doesn't have to be really detailed, doesn't have to be really flowy. You just have a business question, you've got some rules to support your business question, and here's your answer. Everybody good with that? You guys are pretty good with the writing. I'm not too worried. Any questions about the assignment? Let's do that. Let's be honest. How do you guys even started the assignment? Don't raise your hand. You're like, nope, don't have any questions. Might have something about 6 o'clock. If you do, email me. This one shouldn't take you too long to do. All right. If you don't have any questions about association, then today we are going to talk about, so in your textbook, the focus is just on the naive Bayes classifier. However, your software does so many more things than just the naive Bayes classifier. There's a whole set of Bayesian networks. So we're going to do 2 things. Number 1, we're going to focus on understanding the idea behind the naive Bayes classifier. And then number 2, you're going to get to play with all the different options in the software with the Bayesian networks. And I'm going to kind of give you a very brief, high-level idea. I'm not going to expect you to know them, but just kind of tell you a little bit of difference about them, give you some exposure so that if you see this, hear this, you have an idea. But the focus is really going to be on the naive Bayes. So that's where we are today. We're still following our Christian process because I like it. I'm not saying that when you have an exam in a couple of weeks, this is going to be on it. But this is going to be on it, right? So knowing these steps, you've seen them a lot, even if I kind of flash through them, these are really important steps that we've been going through. So the first thing, because I'm really not original, and I'm really still trying to figure out my business question, I really want to know, how do I have a competitive auction with eBay? We're only going to do this one more time. By the end of this, we're going to figure out the best model to figure out our options for eBay are going to be competitive or not. So it's going to be the same data, and this will be what we use for the example. Here we have a few more business questions we can answer. And I'm going to be honest with you. You are learning this for a week. This is the fourth time that I've taught this class. I am still learning things about naive Bayes and how to teach it better, more information, how it works even better. So I don't expect you to know all the ins and outs of this. Just a general idea. If I did come up with this today, because I know some of you really are going to like, Dr. Kiefer, I want to know more. If you want to know more, see how I do that? First of all, there's a chapter in your textbook you can read. I did find, so it's Data Science for Business. It actually has a chapter kind of on naive Bayes, or Bayesian analysis. Actually kind of interesting if you want to get into the math aspect of it. And this is a real easy read as far as the math goes. But the naive Bayes, basically what it is, it has a lot to do with probabilities. And if we can actually start to find probabilities, then we can ask questions about these probabilities. And I started out being very exact about this. But then the more and more I read, and the more and more I learned about these classifiers, we have to be very careful making decisions. Okay, so we're going to be calculating probabilities. But in most cases, this naive Bayes isn't used to actually come up with the probabilities to make decisions if something happens. It's really used more just as a classifier. So our big goal with this is going to be classification. So even though I have some probability questions, really our big goal is still just going to be classification. But by the end of this, some things we may be able to answer are the factors that are most important for deciding if we're going to be competitive or not. Can we identify factors that increase the probability of having a high closing price? Right, that would be cool. Right, I'd like to figure out what helps me have a higher closing price. And then just because this one was interesting to do, the probability of currency change based on category and competitiveness. Right? So does the probability of who's buying, what currency is being used to change, given a couple of different variables? We'll just kind of look into this and see what happens. So our business understanding, we're still working with our eBay data sets. Our data understanding, we've kind of already explored the data, so we're good there. The data preparation phase for our naive Bayes. This is the only time that you're going to see this. But for this classifier, everything has to be categorical. All of the data. The targets and the predictors. Target and predictor. All of the data have to be categorical. Now, if you have numerical data, you have to change it and bin it into categorical data for the naive Bayes classifier to be able to work. We won't get into the data, or we'll get into math a whole lot. We'll do it a little bit, and I'll show you why this is so important.
Would I assume the software will be able to do that? Or?
Yeah. So let me pull that back for a second. Yes, Sassify can. SPSS Modeler can. The problem that we run into with can doesn't mean it does it the most intuitively. So will it bin everything for us? Absolutely. But you'll see in some of my output that I have, the bins are like, yes, let's look at 2.8 to 6.9. And they're like weird. So if you want it to make more sense and be more easily interpretable, you may want to control the bin size. So, yes and no. So let's learn a little bit about this naive Bayes thing. It's going to have a target variable. So supervised or unsupervised? Supervised. There you go, you just got one quiz question, right? Okay. Like I said, all of our variables is going to be categorical. So we've got a classification or estimation. Classification. Especially since I keep saying a naive Bayes classifier. It's a classification thing. It's data driven, so it's all based on the data that we have. We've got good data, bad data. This is how we're going to drive it. There's no model, there's no underlying assumptions we have to meet. And really our big thing that we're going to do is we're going to be using conditional probability. Conditional probability. Quick question. And preset cutoffs. Okay. So you're going to see conditional probability. How many of you guys know what a conditional probability is? got one. I got two. I got maybe.
I feel like intuitively, kind of makes sense.
So intuitively, it kind of makes sense, right? Conditional probability. I'm going to make a probability based on some condition that I already have. Right? So we're going to be doing conditional probabilities. You'll see that here in a second. So our big goal is, again, we're going to estimate conditional probabilities for each predictor given a specific class. So one of the cool things about the naive Bayes is it lets you have as many classes as you want. Right? So in some places we've been really focused on just binary. Pass, fail, true, false, yes, no. But this will actually let you, the math works and is extended to hit any kind of classes we want. So if we want to find yes, no, and maybe. Or if we want to find first, second, third. Whatever we want to find totally works as long as it's a categorical variable. So what we're going to do is we will do some conditional probabilities. We actually have to multiply all these probabilities together. Given a few, we're going to make some pretty big assumptions here. Then once we have these probabilities, we're going to assign our individual records to the class that has the highest probability. And again, are you going to have to do this? No. That's what the software is doing. This is the idea of what's happening. We're calculating all these conditional probabilities, figuring out which probability makes the most sense, and then that observation will go into the appropriate class. So, before we get into the math, one of the ways to think about a conditional probability, or one of the ways to think about this Bayesian rule we're about to talk about, we're going to try and find, and we've got two different things. We have this thing called this exact Bayesian classifier, and then we have this naive Bayesian classifier. And to find an exact Bayesian classifier, what we're going to do is we're going to take our data set, and how many of you guys are familiar with pivot tables? This is where if we've done our job, everyone's hand goes up. I'm pretty sure you guys are all in 5103. We took pivot tables. Okay. So everybody knows about pivot tables. So basically, an exact Bayesian classifier is basically like a big pivot table. So if we have a couple of variables, then we would find the pivot table. We would see where, and we basically just calculate probabilities, right? So this many out of the total, this many out of the total. So let's say we had, let's go with some examples. Somebody give me some variable. Has to be categorical.
Hair color.
Hair color. Somebody else give me a variable. Has to be categorical.
Eye color.
Eye color. Okay. Hair color and eye color. It doesn't have to be crazy. Hair color and eye color. Okay. So we have hair color across the top. We've got eye color across the bottom. And if I went around here, I could classify everybody into one of those categories. Hair color, eye color. Right? You would fit into one of those boxes. You'd have a certain hair color, a certain eye color, pivot table. And then I can calculate the probabilities. Your hair's so buff. Is it red? Is it brown? It's got a little red. Maybe it's because you're wearing red. Okay, well, it's got hair colors, right? So you got kind of, you've got a little bit of a red. See, now it's hard because we're talking variations. Maybe we should go with black. Black's a whole lot. Yeah, black's a whole lot easier. Right? You got black hair, right? So we got black hair. We find everybody's got black hair, and then we start looking at their eye color. Brown. Brown? Green? Not brown. Back here, I can't see. She's got the glasses. They actually kind of look yellow. It's a little purple. Actually, kind of looks purple because it's got your screen. Right, so we're finding all the colors, air colors. You've got everything set up. So then we can actually calculate the probabilities, right? So out of the 20 people in the room, we've got 5 people with black hair and brown eyes. 5 out of 20, right? Probabilities. Easy enough. Using the pivot table to find probability. But now, let's say that I'm looking for blonde hair, blue eyes. Anybody have blonde hair, blue eyes?
Sure.
For this example, no. Right? We don't have anybody in here for blonde hair and blue eyes. that doesn't fit. We're missing that data point. So how can we calculate a probability? We don't know what's happening here. But do we have anybody in here with blue eyes? Okay, we've got a couple of blue eyes. Do you have anybody with blonde hair? I know, we got a little okay. So maybe it's not the best example. Okay. But if we could look at things, instead of looking at a pivot table where both of these variables were combined, and we had to match somebody specifically, what if we just looked at hair color as one pivot table, and eye color as a different pivot table, and we assumed that those two things were independent? Now I can figure out the probability that somebody has blue eyes. And actually in this data set, now I can really figure out the probability that somebody has blonde hair. And so I'm making an assumption of independence, and these two things are totally independent of each other. And when I do that, then I can just multiply the probabilities together to get a probability of having blonde hair and blue eyes. So instead of having to have a pivot table where I have all the information, right, what happens if we picked 3 variables? Blonde hair, blue eyes, wears glasses. Okay. Now I've got a 3-dimensional thing. I've got to find somebody who exactly meets that. That's what the exact Bayes classifier does, is it goes through the data and it has to find somebody that's exactly like you, and then they'll calculate the probability. What's hard to find? So the idea of the naive Bayes is we make this assumption of independence, and we say, you know what? We're just going to look at hair color, and we're just going to look at eye color, and we're just going to look at if they have glasses or not. We'll look at these 3 things separately, find those probabilities, we'll multiply them all together, and we'll see what the real difference is. So I have an example here in a minute where we'll see how far off our real difference is. So this is basically our goal. We're going to be calculating these conditional probabilities. Whichever class you belong to the most, that's where you're going to be assigned. So conditional probabilities is to start. How many of you guys have heard of naive, or just the Bayes rule? Brilliant. I love when you guys don't know a lot of stats because I can screw up and you don't know. I'm just kidding. I actually went through really hard to make sure I got the math right. So the last time I taught this, I didn't, and it was embarrassing. So there's all these formulas for calculating probability. You go into a probability class, you spend all this time learning about sets and how this event talks to this event and how these things calculate. So I tried to find, and this was me just Googling, finding the best example of naive Bayes that I could find. So we have 14 data points over on the left. We're looking at the weather, and my classification variable is going to be if I play or if I don't. This is actually, we went out to play golf. I don't golf, so I don't know how much the weather affects people. I see people out in all weather playing golf, so how do you guys golf? You go out and play in the weird weather, don't you?
Yeah.
See? So this may not really be true at all. Okay, but what we have is we have the weather and we have if you play golf or not. So you'll notice out of the 14 times, there's 5 times you didn't play golf, or 36%. And there's 9 times when you did play golf, 64%. That's just the probability. Easy enough. Good there? Okay. The next thing says, let's say I have some more information. Maybe the weather does matter. Okay? So now let's see if the weather is overcast. So how many times do we have the weather being overcast? 1, 2, 3, 4, right? So 1, 2, 3, 4. Okay, so 4 times it's overcast. And when it's overcast, what's the probability that I went and played? 100%. Right? So if I know something about the weather, now I can change my probability. This is a conditional probability idea. If I know something about the weather, now I can change how likely I am to predict correctly if I'm going to go play golf or not. Okay, so this is kind of what happens. It starts out with, how many times am I going to say yes? 64%. Then how many times is the outlook overcast? 4 out of 9 times. So I'm just looking at the yeses. 4 out of 9 times it's overcast, and I went to play. And then totally, when it's yes and overcast together, 4 out of 4 are 100% of the time. Right, so every time it's overcast, I go out to play. And so this is the idea of the conditional probability. So the math itself, I've got formulas just hanging out on the top of the page if you really wanted to get into it. So we start out with A, our event A being yes. Our event B is if it's overcast or not. So the probability of yes, we said was, this is kind of little, but you guys have it, is 9 out of 14, 64%. The probability of B, so the probability of it being overcast, is 4 out of 14, or 28%. Then to figure out the probability, and I'm looking at the top right here, or top left, I guess, for you guys, is the probability of B, overcast, given that I went out to play. That line means given. So the probability that it's overcast, given that I went out to play. And so there's a formula for doing this. So this says, well, how many times was it overcast and you went out to play? And then you divide that just by the times that you went out to play. And that tells you something here. So the probability that it was overcast and I went out to play, we already decided that happened all the time. So that was 4 out of 14 times, so that's 28%. We do the probability of B given A, we follow that formula, we wind up that's 44% of the time, which is kind of nice. That's that 4 out of 9 we already figured out. What the Bayes rule does is it basically says, you know what? It's nice knowing if it's overcast, then I went out to play. But really I want to know it the other way around. I want to know the probability that I'll go out and play given that it's overcast. And so there's a different formula for that. And this right here is actually the Bayes formula, this top right. But you'll notice it has this conditional probability in it too. So you've got to calculate 3 pieces of information. And if you've got these 3 pieces of information, then you can actually go in and figure out this other probability. This is kind of the math behind what's going on. Right? So we ultimately ended up with what we knew, right? So when we just have these 14 data points, we can look and figure out that if we know the forecast is overcast, then they went out and played 4 out of 4 times, 100% of the time, and we could just look and see. But how did we actually get that information? We went through these sequence of probabilities. You can do the other thing yourself. So I did it for yes, you could switch it and do it for no. And if you got 1, you're going out 100% time, then when you go no, you're going out 0% of the time, just the common time. So a way to think about it, I should have bookmarked this page. The way that this book kind of talks about it. Can I see if I can remember what page I read this morning? Oh, okay. They talk about it in terms of, and I've never explained it this way before, which is why I'm relying on the book a little bit. They use it in terms of hypothesis and explanations. So if I rewrote this question, would it make sense if I rewrote it as, there we go, the probability, all I'm going to do is just change the A's and B's for different words and see if this makes sense to you guys. So the probability of a hypothesis given some type of evidence. But really it's going to be hard to actually find out the probability of some hypothesis. So we're actually going to look at it the other way. I can figure out the probability that the hypothesis occurs, just in general by itself. Then we can figure out the probability of the evidence given our certain hypothesis. Right? So it's hard to figure out evidence, the hypothesis given certain evidence, but it's easier to figure out the evidence when we make some assumptions about it. And then we would divide it by the probability of the evidence just happening all on its own. This is just another way to think about it. And again, this is the theory behind it. We'll do an example that hopefully will make this make even a little bit more sense. I don't expect you to know the math. This isn't going to be one of those, oh yeah, surprise, the math shows up somewhere. It's not going to. So the big idea that I want you to be able to see is, if we have 3 pieces of information, we can get those. So let's try another example. Okay. So again, our exact base classifier, we're looking for something that has to fit exactly. But we don't always have this thing that exactly matches. So we're going to make some assumptions with this naive base classifier that's going to let us do some math without having to be exact. Here's the calculations. It's kind of crazy. I'm going to skip that. And I'm going to do an example. So the example, this is actually the example from your text. We're going to talk about financial fraud. We haven't really been talking about finances very much. We're talking about financial fraud. Accountants, auditors, maybe. Right? So you're going to go audit and you're going to go find was there fraud or was there not. Okay, so the predictors that we have, very basic, right? We're talking classification variables. So we've got, is there any prior pending legal charges? That's a yes or no. And then what is the size of the firm? Is it small or large? We're going to keep it as a simple example here. So this is the data that we have. We've got 10 different data points. So we are trying to figure out, do they have pending legal charges or not? So there's 4 yeses and 6 nos. We've got the size of our company. So there's 1, 2, 3, 5 large companies and 5 small companies. And then we find out was there fraud or not? So was their earnings statement truthful or was there some type of fraud? So the first 6 are truthful and the last 4 are fraud. And you can start to look through here and figure some stuff out and see what was going on and just try to eyeball it. But that only works because we have 10 data points. If we had 100 data points, it's going to be a lot harder. So for our exact base classification, we would actually go and find data that meet our exact classification. So our goal is to classify as fraudulent or truthful a small firm with charges filed. So we're going to try and find out, if I have a small firm and charges have been filed against me, what's the probability that you're going to be fraudulent? So if we go look at this, you'll notice I have a fun little blue smiley face. Try to make it a little bit easier because there's a lot of data there. Okay. So there's 2 firms that actually match this. They both have charges, they're both small, and what's the outcome? 50%, right? One's truthful, one's fraudulent. So if we go back, then the probability of fraud, given that the charges are yes, the size is small, is 50%. It's a half. Okay. That's the exact base calculation. We had to find something that matched exactly. Now we can move on, and we're going to try this naive base calculation. So instead of having to have the full pivot table and find what exactly matches, now we're going to look at the pivot table for just the small firms and just the one where charges have been filed. We're going to multiply those 2 probabilities together and see what happens. Okay. So our goal is the same as before. But now we've got these 2 quantities. So the first one is going to be the proportion of charges where we're small frauds. Okay? So the first thing we're going to look at, the proportion of charges. So let's look at my little green circles. So we have 4 frauds total. 1 small, 3 yeses. Okay. So the proportion of total, 4 out of 10, we had 1 out of 4 was small, 3 out of 4 yeses. So that's where those values came from. 3 out of 4 times 1/4 times 4 out of 10. So 3 out of 4, 1 out of 4, 4 tenths. So So when we multiply all those together, we get 0.075. So that's the probability for fitting that one. Now we're going to look at the truthful side of this. Okay, so for proportion of things, and now we're going to look at the true. True is going to be green. Okay. So if we look at the greens, I lied. True is going to be purple. Honest, purple. I don't know. Just make sure. Really what happened was last year when I did this, my pen didn't work. And so I had to figure out some way to illustrate this, and we came up with smiley faces. And I thought they were cool, but okay. So now we're going to look at our purple. So how many charges do we have out of all the truthfuls? 1 out of 6. And how many smalls do we have out of all the truthfuls? 4 out of 6. And how many truthfuls do we have total? 6 out of 10. So, 1 out of 6, 4 out of 6, 6 out of 10, 0.067. So now using Bayes' theorem, the probability of fraud, given that we know if there was charges or if it was small or not, we take 0.075, we divide it by 0.075 plus 0.067, and we wind up with an estimate of 0.53. So what was when we did it exactly, what did we get?
0.5.
We got 0.5, right? It was 50-50. Now when we're estimating it, using this naive classifier, we get an estimate of a probability of 0.53. Pretty close? Pretty close. And this was just with 2 variables. That was really simple. The more variables we add, the more complex this equation can get, but it stays in the same idea. You just add in another variable, you just add in another thing you're multiplying, and it works just the same. Okay. So this is what's going to go on behind the scenes as we're going to let we'll do some SPSS, we'll do some SAS-VIA, calculate our neural network, or our naive network case.
So what is worrying me about this is independence.
Mm-hmm.
How much of an assumption is there here when it's like you know they are not independent and you assume it's independent, or there has to be some kind of a discrimination about whether or not they're independent?
So here is the great thing. There are 2 ways to use these results. One way is to actually use that value, use this probability value, as a predictor. And try to say, well, there's a 53% chance that this is going to happen. And when you start doing that, then the independence matters more. So I'm going to tell you to use that with extreme caution. So the probability exists. We use the probability, but the people who actually, and when you use this and see this a lot, the goal isn't to actually utilize that probability. The goal is to classify correctly and to get it into the right classification. So here, we had a 50-50. Maybe I should have had a better example, right? But even if we said 0.5 is our cutoff, then we would classify it in the 1, or in this case, the truthful category. Here, now we have 0.53. Now we're just showing even more that we're going to classify in the truthful category. So we still make the same decision. We just estimated it instead of done exactly. So with the independence, so let's think about if 2 things are dependent on one another, right? So let's talk height and weight, right? So if 2 things are dependent on one another, then you're like, well, if I'm really trying to figure out probabilities, maybe I don't want to do that. But with here, it's going to be like, okay, well, you have a lighter person, you probably have a shorter person. Okay. So all I'm doing with these probability terms, I'm actually going to be overestimating in the correct way, right? And so it actually makes it a stronger case for which classification to make. So in this case, right, so sometimes you talk about overestimation and underestimation can cause big issues. In this case, as long as you just use it for ranking and just putting it into a class, then yes, we're going to overestimate, but we're going to be overestimating into the correct class. So basically, we're kind of double counting that idea, but it's okay. In some places, that's not okay. But for this one, it actually works in the favor of the algorithm. That's a great question. So we're making this assumption, but when we make this assumption, spring break. Had some fun. I'm just kidding. So yeah, so that's kind of the idea. So that's the math. That's what's kind of happening behind the scenes. So again, the exact Bayes, you have to find something that exactly matches. The naive Bayes is awesome because we're making the calculations easier. It doesn't have to be exact. We make this one assumption, and we can do a whole lot more, a whole lot faster. So when we get to the software piece, the naive Bayes is what we talked about. The Bayesian network is going to connect our target variable to all of our different input variables. Our naive Bayes is just very generic. There's no connections. It's just target to input, target input, target input. Do our calculations, multiply them all together. Life is good. No other connections between the variables. Everything's conditionally independent. It's naive. It's the basics you can get. Of course, it's statistics, and people aren't satisfied with just leaving it as the basics you can get. They want to try bigger and better and other things. So we have a thing called a Bayesian augmented naive. And what it does is it actually lets you take your input variable. It has our input variable. And here each node can have multiple parents. So we talk about this as a parent and a child. You can think of that as like a target and an outcome. So in a naive, you have one target for as many outcomes as you want, but you only have that one parent. With this one, outputs can then be targets of other variables. So you start to add this little structure to it. We have a thing called a parent and child. Again, these are just things you're going to see that we're going to play with here in a second. And what we're doing here is it's kind of the same thing. Our input variables can either be a parent of the target or a child of the target. So here now kind of the target gets to go into the middle. We have a diagram we're going to look at. The target can kind of go into the middle, and it can either be the start or the end or somewhere in the middle. We have things, it's called a tree augmented, right? So we talk decision trees. You're like, why not put a decision tree and an naive Bayes together? It'll be fun, right? So it has our target variable. Each input variable connects an input variable to the tree structure. Each node can have at most two parents, one of which has to be the target. So it's kind of, it's like, yes, I'll let you have multiple parents, but I'm going to limit it. And you have to have at least one as the target. And again, these are just going to be kind of different ways that you're just calculating probabilities. So when we're talking about conditional probabilities, when you think parent and child, it's what can be a factor in that conditional probability. The Markov blanket, I'm not even going to get into, but it's an option you can choose. So ultimately, like I said, this is a classification thing. So if you're looking at the fraudulent versus truthful, if you're looking at an airline, anybody fly over spring break? Right? Hopefully you got, I was going to say, how many cancellations did you have? Right? So you're looking at delayed or on time. Naive Bayes, when you talk about this one right here, so spam, you guys have a spam folder? Whether it's called that or not. Trash, whatever it's called. Right? Spam versus not spam. If you get into, you could actually look under the hood of Google and Mozilla and all the different, they actually use a naive Bayes classifier coupled with natural language processing to decide if you have spam or not spam. That's the way that it's working. It's calculated, it's looking at the words in your email. Yes, it's looking at the words in your email. It's looking at the words in your email. Some of them look at the actual text, some will look at just the headlines, so there's different ways that it'll look at it based on privacy. But it looks at certain keywords, and based on the probability that this keyword is this spam word, then it throws it into your spam folder. So, all along, you've been relying on naive Bayes, and you So, what you're going to be doing for your assignments, you'll be going into both SAS VIA and SAS Enterprise Minor. You're going to add on a Bayesian, so BN, Bayesian Network Classifier. And when you do that, there are 4 different options: the naive Bayes, the TAN, the band, and Bayesian network. So these are the ones that I just kind of have on the screen. And really your idea is just going to be to explore them. For this assignment, I pre-made a chart for you that you have to fill out.
So for the decision tree network, you don't actually have to add your own.
No, it's already done for you.
Can you build it off of one you created?
Yes, as long as you tell me that you did that, absolutely. Right, so you could, and that'll be the thing, it's called an ensemble. There's actually an entire chapter about it, of where you put a linear regression or a decision tree in front of a Bayesian classifier. I'd probably do a decision tree in this case. You could put a decision tree in front of a Bayesian classifier, and then the decision tree will pick out your top best models, or your top best variables, and then take those variables and put it into your naive Bayes. In fact, next week, I will definitely even recommend that almost any time you do a neural network, so the Bayesian networks kind of have this idea of importance. You'll see that when we get to our SPSS output. They'll kind of take the predictor performance. Say, these are good predictors, these aren't. Neural networks don't do that. And so neural networks are very sensitive to the variables that you put in, because it's a learning kind of idea. And so I'll put a decision tree in front of a neural network to help with variable selection all the time. So you can do the same thing here. Absolutely. This is kind of the output. This is what I was kind of talking about. All it is just a visualization. There's no value. There's no real interpretability from this. It's more just a visualization of seeing how the network was created. So here, the variable that I have for a target is called income. And you can see that some of the variables are coming into income, some of the arrows are going out of income. Here we have multiple arrows going in, so this is not just a naive Bayes. The naive Bayes, you just have the target, and everything's coming out of the target. So this is one of the other models. We're not going to get into which one, because it doesn't matter. But you can start to see connections between them. So like for some, they're only connected to the target. But if you look at the top, kind of top right, you see relationship and age. Those two are connected with each other. So there's some type of conditional probability that's being allowed there. For our visual analytics, we have our Bayesian network. You're going to have the option to use variable selection or not. You're going to have the option to do, we have naive Bayes. This is the TAN, the parent-child, the Markov blanket. So they're named a little bit different. There's just different options that we have. And again, the idea for this one is just going to be exploring and seeing what things are different, seeing which model works best. And then if you really want to understand what's happening, you can get in and understand it. The cool thing about what's going to happen with your assignment, what we're going to do even with our eBay auction, is that you don't have to understand all the stuff going under the hood to find the best classifier. Once you find the best classifier, it's usually a good idea to go back and see what's going on underneath the hood. But you don't have to know all the ins and outs going in. This is kind of the look you're going to get for SAS VIA. So again, I have income. And you'll see I have arrows both coming out and going into income. Okay, so again, this one isn't going to be a naive Bayes. It's going to be one of the other ones. They selected as the best model. SPSS Modeler does naive Bayes as well. We partition our data. We have a Bayesian network. Get some results. Here they only have the structure type. We only have 2 different structure types to try. Okay. So different software, different advantages, different weaknesses. You're still going to get, as always, your misclassification matrix, your false positives, your false negatives. All that still shows up in any software that we use. This one I picked because this was the naive Bayes output. And you'll notice it's the no, it's not. It's the TAN output. I lied. Because we have target, and the target goes to all of these different variables, which you'll see that some of them come in and then go out again. So there's always a direct connection between the target and a variable. But here we have some other variables or outcomes that are still related to other outcomes. And again, it's just a visualization of what's happening. The cool thing about SPSS that I really liked until I learned more about the ISYS phase, right? I'm like, oh look, here's all the probabilities. Probabilities are great. Now I can start interpreting them and using them to make decisions. Until I learned that you shouldn't use the probabilities to make decisions. Okay? So it's fun to be able to kind of see what's happening, to see how the choices are being made. But you're going to use this just for classification purposes, not for actually, let's go and make a decision on this. Okay? So here, I'm looking at, given someone's relationship. So what this is an adult data set. I'm trying to figure out their income. It's my target variable. But even here, you'll notice I don't have my target variable in this set of probabilities. Okay, so the set of probabilities I have is I have the relationship, I have my income's right there. So I have the relationship, I have the income, and then I have the probability if someone is a male or a female. Okay, so based on the data set, and I picked this one because it seems more obvious. In this data set, if someone is classified as a husband, okay, data set specific, if somebody's classified as a husband, really doesn't matter what your income is, your probability of being a male is 100%. You're like, yeah. Okay. If someone is classified as a wife, right? So in this data set, if someone is classified as a wife, no matter what your income is, your probability of being a female is 100%. Now, so I'm trying to remember all the details about this data set. I believe this data set is about like the income of U.S. servicemen and women, and how it relates to beneficiaries, I think, because that's where some of this other relationship comes in. So you're the beneficiary. So you are, let's say that you're unmarried. Okay. So if you're unmarried, write it down, and you have, we'll consider that a high income, so it's greater than $50,000. Are you going to be a male or a female? You got 0.45 and 0.55. If our cutoff was 0.5, then class-wise, we would classify you as female. Okay. But it's kind of close, right? So this is one of those where you can say, like, yes, the class is going to be female, but maybe we're a little more interested. Okay. So we'd still say you're female. If you're unmarried and you have low income, now what are you going to be classified as? We got a 0.2 and a 0.8. Now we're strongly female. So what does that tell us? In our data set, the probability, so where are we going to find, aside from being a wife, where's the most likely place that we're going to find a female? Unmarried with low income. So again, we're not going to make huge business decisions based on this, but this does provide you a little bit more insight. Okay. Where else do we see a large, I know it's kind of tiny, anywhere else we see kind of a large probability?
Not family.
Not family?
Or,
So if you're not family, and you've got a high income, probably a male. So we can actually, like I said, it's kind of fun to see these are the probabilities going on behind that relationship right there. So, two things that I'm going to tell you. Number one, be able to read this. Number two, don't use it to make good decisions. Okay?